Good. So I'd like to welcome everyone to the second C's Colloquium. Today it's my pleasure to introduce our speaker today, Jason Briner. I met Jason when I gave a talk at Lamont last spring when I brought up my historical geology class up to Lamont for the day. He contacted him because, when you give a talk at Lamont, it's not for, he's talking to some of the best scientists in the world. So I asked them to send me a paper, maybe some slides, so I can prepare my students better. And of course, he graciously sent papers and slides and everything else. It was there that I started learning more about his incredible research that he and his team were working on. So he started off just only 14 years ago, young whippersnapper for some of us, and got his bachelor's degree in geology in 1996 at the University of Washington, master's at the Utah State University, and then his PhD at the University of Colorado at Boulder. And since then, he's just been doing really amazing cutting-edge research, looking at basically late Pleistocene glacial chronology and history. Then he became a professor in 2005 at the University of Buffalo, which is SUNY. And he's been doing cutting edge research in Greenland and in other places, understanding the processes, the timings of glacial changes. He uses a lot of different methods that he'll be talking about. And one of his latest papers is in Nature, and it was basically on the rate of loss of the Greenland Ice Sheet. And so I'm sure that he's going to be talking at least a little bit about that, if not a lot. And his talk is entitled today, "The Rate of Ice Mass Loss in Greenland Will Be Higher this Century Than Any Time in the Past 12,000 Years. How We Know." Welcome, Jason. You got the floor.
All right. Thank you so much for that really nice introduction. It's really my pleasure to be able to talk to you all today and to get to know some of you as well as can be achieved over Zoom. So thanks everybody for your patience with the times that we're in these days. And it is exciting for me to get to talk about this particular research. It will be coming out in Nature, this story that I'm going to tell you about today, I believe, at least so they say. And Dr. Leah Lesnick, who will soon be at the institution, was part of this work. And so I'll get to share with you a little bit of her piece to this big puzzle. You can see a long list of names in the bottom there. And because this work was highly, highly collaborative. It was just a pleasure to do this work. We've been working on this for the last 5 years or so, and we had a giant science team that we got to do this work with, and I'll be explaining a little bit of that as the talk goes on. So first, a little bit about where I'm at right now, the University at Buffalo. Of course, everyone there, probably Buffalo, New York is in the opposite corner of the state from you guys. We're up here where the land of the chicken wing affects snow. Our department, I just wanted to mention, it is a SUNY university. It's one of the 4 SUNY universities. And we have a geology department here that's about 15 tenure track faculty. There are a couple of other clinical faculty and a couple of other research faculty. So there might be maybe 20 professor types in our department. We have about 45 graduate students, a lot of master's students with fewer PhD students, but maybe like 10-ish PhD students. And we have about 75 undergraduate students pursuing degrees in geology or science or Bachelor of Arts or minor, things like that. The research that the faculty in our department focus on is largely around hazards, both natural hazards and human-caused hazards. We have a group of volcanologists, physical volcanologists and hazard science, maybe 4 to 5 faculty in that group. Another big research emphasis in our department is environmental science. We have hydrology and near surface geophysics and contaminant hydrology and geochemistry. And then the other main group is the one that I'm in, which is on ice sheets and climate. And what are we now? 5 faculty who study ice change in paleoclimatology and things like that. So I just wanted to mention to the audience, faculty or student, that if you're looking for a place to maybe continue your earth science education and you want to think about graduate school, you can come out to Buffalo and stay in state. And if you're interested in any of these research topics, I just encourage you to check us out. We'd love to hear from you, and we're always looking for talented undergraduate students that want to pursue a graduate degree in geology. So the concept of today's talk is about ice sheet change and reconstructing how ice sheets change through time and trying to splice the geologic knowledge of how it's changed in the past all the way up until today to blend it in with the observations that we're making today of our ice sheets. And so I'm going to start a couple of slides about the present situation of the ice sheets. And probably a lot of you are aware, of course, these series of maps from the 1850 to 2010s at the bottom just show a visual way to kind of blur your eyes and step back and look at the warming of our planet. A detail that maybe isn't as easy to pick up on these maps is that out of the spatial pattern of warming on our planet, it's the Arctic that's taken the biggest hit. And it's in the Arctic, of course, where there's a lot of glaciers and ice sheets. And so here we are walking across the surface of Greenland a couple of summers ago, and there's just a lot of meltwater everywhere. Of course, melt is a natural part of the ice sheet process. Even glaciers that are in balance with still have a melt season. But if we look at the charts, the knowledge of that melt, we can tell that melting that's happening today is occurring at a greater rate, and there's more meltwater than average, than normal. And so it's definitely some healthy ice sheet. These two graphics come from a really nice website from the National Snow and Ice Data Center, this Greenland Today website. And you can look on this website any day, and it shows you a map on the left of basically the cumulative melt of days that each of these pixels that you're looking at has experienced melting. So these pixels kind of grow and intensify over the summer, and then there's not much melt in the winter, of course. And then on the right is a seasonal plot. So it runs from April to October along the bottom. So that's the melt season in Greenland. And then it's the extent of melt. So like the areal extent of the ice sheet that's melting. And the blue line background is this median line. That's the normal amount of melt maybe that occurs in a typical melt season in Greenland. And then you can see in the current summer that we're in right now. I guess summer's almost over, sadly, but September is a good month. We like these first cool days are really nice. And for Greenland, it means that the melt season is coming to an end. And so this is a chart that I just downloaded late last week, bringing us into September. And you can see the red curve is quite a bit above the blue curve, almost all the way throughout the melt season. So it turns out 2020 was a really big melt year, the Greenland ice sheet. We also know from various records that 1981 to 2000-ish was the Greenland ice sheet with neutral balance. It wasn't growing and it wasn't losing on average. And so this blue line also represents that's where maybe a healthy ice, and anything above that blue line is an unhealthy ice sheet. So this ice sheet is experiencing a lot of melt. We can look at that in terms of melt rate, and that's what this plot shows. All these vertical bars is the rate of mass change of the Greenland. This was a paper that came out last winter. And it was the first, no, not the first, but it's the most recent synthesis of a bunch of data and estimates about the rate at which the ice sheet's melting. So the vertical axis here is in gigatons of ice per year. That's 1 billion metric gigatons of ice per year. So that's a rate of mass change on the ice sheet. And anytime the data are below this horizontal line at 0, the negative rates, that means the ice sheet is losing mass. And you can see that these data bars hover around 0 until maybe the early 2000s, and then they really deviate from 0, and they reach a maximum ice loss in 2012. That's this bar right here under my cursor. And then the rate has been negative, but not quite as negative then. What I just showed you, 2020, this current summer's melt, is not on this plot, but it's down, actually nor I think maybe is 2019, I forget. But the 2020 season is way down here now. And so it's comparable to these levels, these rates of mass loss around 2010, 11, and 12, something like that. So the trend here is, unfortunately, we don't exactly climb back up to 0. The last couple of melt years have been as low as some of the lowest in this data series. Looking at that a different way, in the last plot, it was just the rate of mass loss or mass change. In this plot, what these scientists have done has, this is a different record based on a gravity satellite, but this is if you cumulate those mass loss rates and just track the mass that's lost through time. In this case, from about 2003 up to 2016, 17. And if you make the plot cumulative, not just the rate through time, but if you add up the next year's mass loss with the next year's and the next year's, see this disturbing trend in the mass of the Greenland ice sheet. There's the seasonal flicker back and forth, but overall the trend is down. And that's really concerning for obvious reasons, right? The Greenland ice sheet has over 7 meters of sea level equivalent within it, 24 feet of sea level equivalent, and that is getting dumped into the ocean, and so here, of course, is the sea level rise. Greenland, you may know, is one of 2 ice sheets we have on the planet. The other is Antarctica, and if you follow Steve's work or some of the other work, you know that the Antarctic ice sheet is way larger than Greenland, maybe 10 times, 9 times as big or something like that. And the Antarctic ice sheet is vulnerable too to climate change, and it has been contributing to global sea level, but it turns out Greenland has been contributing about twice as much. So it's the smaller ice sheet, but it's the one today that's really contributing a lot to sea level rise. That plus mountain glaciers and plus the thermal expansion of seawater due to a warmer atmosphere. But in any case, the Greenland melting piece is a really important part of the sea level rise equation right now. What I want to talk about now, of course, though, is that, yeah, we have observational records of ice sheet change. We can have a number of sites point their sensors down at the ice sheets and understand how ice sheets are changing today. What we have less data on are how ice changed in the past. And we have moraines and glacial dirt and things like that where we can reconstruct ice sheet changes. But typically those kinds of reconstruct produce something like a gigaton per year of ice sheet change 5,000 years ago. They're kind of coarser than that. They're not it's harder to quantify the field of glacial geology. So what I'm going to talk about today is how we do glacial geology and then how we turn that into some numbers so we can blend the history up to today's observational records. So in the outline today, I'm going to talk about exploring Greenland's past. So just a few slides about the history of the Greenland ice sheet in the last 10 or 12,000 years. And then what my group has been doing in reconstructing the ice history and some of the tools we use. And then I'm going to, the third chapter of the talk is talking more about what's in this publication coming out in a couple of weeks about blending the past in with the present and even projecting it into the future. So let's start with exploring Greenland's past. So this is a plot of temperature on the left there. And in this time, and in this configuration, time is on the vertical axis, is at the top. And this just goes back 8,000 years. But I show it for a specific reason, and that is to show that even in the current interglacial period, the Holocene, has been climate change. There was a period in the early part of the Holocene that was warmer than it is today, or at least prior to the 20th century period, which we call the pre-industrial. So earlier than the pre-industrial, we had some climate oscillations, and we have this period in the earlier Holocene that by all accounts was warmer than today, or at least warmer than the pre-industrial period by maybe like 3-ish degrees, something like that. So when we are interested in reconstructing the history of the Greenland ice sheet in the past, we're particularly clued in to how did the ice sheet respond to this period of warming. And some people have argued that that prior warming might be analogous to what we're looking like in our future. So there might be some things to learn about how they responded to climate back then. So our research targets two main questions that I'm going to talk today. So the first is, what was the pattern of Greenland ice sheet change during the Holocene? What were the rates of its recession, or were there any episodes re-expanded, things like that? And then this other part that I've been mentioning a couple of times now, how do today's rates of mass change compare to the rates in the future? And this is where, to answer this, I'm going to talk about this third piece of today's outline, where we blend all those time scales together. So the field area where I've spent my last maybe 12 years or so working in Greenland. My group has the luxury of going to Greenland every summer or so for the past dozen years. And we've worked up and down this part of Greenland that's seen in the box. So west central Greenland and southwest Greenland. And you can see that the ice sheet on Greenland doesn't smother the entire island, but there's a strip of land between the ice sheet margin and the ocean. That's this like light green color stuff down in here. It's on that land where there's available geologic evidence of past ice sheet change. And that's what my group has been exploring. For example, if you look, sorry, I forgot to put a little box here, but if you look in the middle of this tall rectangle, maybe like right, I'm going to show you a map. So here's the ice sheet on the right side and the ocean on the left side. And this is that strip of land between this and sea. And these colored lines are moraines that we've used to reconstruct the former ice sheet. This figure itself was done by Alia Lesnick, and it's in one of her papers. She compiled moraines that were mapped long ago by a Danish geologist named Anker Weidick. And she did a bunch of new mapping and digitized everything to make this old work along with new work all like GIS compatible with the latest projections and put online in a database. So now these moraine limits, these ice limits, are available to the public and other scientists who want to compare their results with these moraines. In this series of moraines here tells us that the ice sheet used to be, during the Ice Age, the peak of the age 20 or 15,000 years ago, the ice sheet was off into the ocean. It terminated in the sea over here. And between then and now, the ice sheet has steadily reached back, and back. And it turns out it retreated to some position inland that was smaller than it is today, and then advanced back out. And we know that because in fjord environments, like up here in the northern part of this image where there's this long fjord that comes all the way in, places where the fjord goes all the way up to the modern ice front, the re-advance of the ice picked up ocean sediments with like mollusks and seashells and put those in the moraines. And we can date those things, and they date like 2,000-4,000 years. So we know that there used to be open ocean water where the ice sheet currently is sitting. So overall, we know that the ice sheet retreated to its present position a little further inland, and then it kind of came back out. And so one question we have about this pattern is, when did all these take place? And so one of the main methods that we've been using to place a history or a timeline on the ice sheet changes that are per landscape is called beryllium-10 surface exposure dating. Beryllium-10 is a cosmogenic isotope, much like radiocarbon is in the atmosphere. Radiocarbon dating is also based on cosmogenic isotopes. And these isotopes are produced in the atmosphere or in the Earth's crust when certain target elements are bombarded by cosmic ray particles from outer space that just constantly bombarding our planet all the time. And they have a new suite of isotopes, and we use one called beryllium-10. Beryllium-10 is also produced in the atmosphere, but we use the type of beryllium that's produced in rock. And the concept is basically like the longer a boulder, like this one under my cursor, the longer that boulder exposed at the Earth's surface after the glacier deposited it, the steady buildup of beryllium-10 occurs in its surface, like in the upper maybe 10 centimeters of that boulder surface. Beryllium-10 just accumulates in there like a suntan. Like this boulder's been out tanning for 10,000 years, and beryllium-10 has been building up in that surface. And the concept is that when the glacier first deposited that boulder, actually like this is a very young moraine, actually. This moraine was deposited maybe 100 years ago. So the geologic clock has just started. And now these rock surfaces are exposed to the cosmos for the first time. The clock is starting to begin. And the tan, if you will, is starting to on the boulder surface. And by the time you get that moraine maybe ages 5 or 7 or 10,000 years, here's an old moraine that dates to the early Holocene. It's a landscape that's largely bedrock, like in the background. You see all the rock that's just sculpted, the glacier sculpted that bedrock. There's no moraine on it. And now and again, the bedrock is draped with a pile of till, these moraine ridges. And the boulders on the surface or on the crest of this moraine ridge may have been sitting there ever since the moraine was deposited. So these boulder candidates for exposure dating. And we want to measure the beryllium-10 concentration in the surface, and then we can invert that for age when we know the rate at which and those values come from other studies. So we spend a lot of time in the field mapping and then sampling a lot of boulders. So we do that with a little angle grinder saw, like that's me just kind of doing a little saw work on the boulder. And then we get a sledgehammer and we bang into the rock after we've maybe loosened things up with the saw cut. So it allows us to get like big chunks of rock coming in. Put those chunks in baggies and bring them back to Buffalo. And then we dissolve the rock in our lab and extract the beryllium, and then we send that to an accelerator, and it's the concentration of beryllium in there, and we can invert that for age. So I'm going to show you how we've been using that dating method to reconstruct ice sheet history. Back to this map. So these are the places that we've been visiting. So we'll take a helicopter out to a camp, and we'll camp out and sample, and then we'll move and do it again. And so we've been able to date all these different ice limits that you see here. We go to places where those moraines are bouldery. It's the boulders that allow us to date the moraines because, and the larger the boulder, the more stable it's been since it was originally visited. You might imagine that a lot can happen to a moraine in 10,000 years or 7,000 years. So of just erosion and degradation and things. So we try to find big boulders that are tabular, that are likely to have sat on the surface ever since they were deposited. That's the idea of what we do in the field. And this is a map of one of the moraine limits that we've dated. And the ice was in the lower right and flowed towards the left. And each one of these dots represents a boulder that we dated. And these are the ages, the M10 ages that we got. And of course, I'm showing you an example of where it worked really well. You can see that there's hardly any scatter among boulder ages. There are other cases where we may date the same number of boulders, 5 or 6 or 7 and they may range by 1,000 years. And we just take them, the average if we can, and use the average age. In this case, the average age is really tight. We got lucky with these boulders. So what I'm going to do now is show you some data. And yes, okay. So here's an example. This is one of the, like an age plot that we would use to represent moraine ages of individual boulders. So each one of these probability distribution curves is a single boulder age. And these are just Gaussian curves that represent the mean standard deviation of a measurement that we get from the accelerator that we turn into an age. That's why they're Gaussian, because they're based on isotope measurement statistics. And then we can sum those individual boulder ages or probability curves into one summed probability curve. And that gives us an average age of this series of boulders that's 11.6 with a 1 sigma range of 400 years or something like that. And we've done that. See, this is a tighter, taller Gaussian curve because this is that really tight cluster I just showed you in that last slide. We got really lucky with that one and other ones. These are, by the way, the 5 moraine limits that I showed you earlier in Aaliyah's map. And so we were at date, and it's backwards. If I would have done this again, I would have drafted it differently. But in the map, the oldest moraine is on the left. Here, the oldest moraine is on the right. Sorry about the switch there. But you get the idea. The oldest moraine is 11,600. Then there's one at 10, one at 9, one at 8, and one at 7. Elsewhere where we've worked, this main series of values is on one transect in Aaliyah's map that I just showed you, but we've worked in other parts of Greenland, and we see the same moraine ages repeated place after place. So we have a lot of confidence that these are regional moraine ages. And what we can do with this information, is make time distance diagrams. So this is the glacial geologist's kind of summary chart of their results. We're back to where old is on the left and the ice sheet is on the right in Aaliyah's moraine map. And this has age now. This is an age distance plot. So 12,000 years ago, and then time, as we go up, time is getting younger. And then on the distance axis, we go from the outer coast up to maybe 160 kilometers inland from the coast, which is where the modern nitrogen is. And each one of these dots is one of those moraines. And the line between the dots is our best guess for what the ice sheet margin did. So the Greenland nitrogen in southwestern Greenland retreated onto land maybe between 11 and 12,000 years ago. And then it marched, the ice smaller and smaller and smaller, and maybe had small little re-advances to deposit those moraines. And then at some point, it goes smaller than it is today. That is dashed. So we have a question mark about how, we don't know how far inland the ice sheet went. And then, but we do know that it came back and deposited a couple of moraines just 100 or 200 years ago during that little ice age cold period, which is a cold part of the Arctic that between 500 and 100 years ago, something like that. Okay, so we've built our time distance diagram. We know what the ice sheet mark did, at least between maybe 12 and 7,000 years ago. We have a little bit of a question mark about what it did in between 7,000 years ago and maybe 1,000. So we used a different approach to fill that gap, to fill the gap of where was the ice sheet when it was smaller than it is today. And to do that, we investigate lakes, and in particular, the sediment that exists in the bottom of lakes. So much like in the same concepts in paleoceanography that a lot of you guys do in your department, by that sort of paleoclimate core work in lake sediment cores. And in this particular application, you can see the ice sheet, the Greenland ice sheet up horizon. You see it up there? Nice blue sky day. And here's the ice sheet draped over some of the mountains up there. And, you know, if you were to get all the way up on the skyline and look east, you would just see ice forever, all the way up to the summit of Greenland, if you could see that far. And here the ice has spilled over a mountain range here, and then there's a little ice lobe coming down the other side towards the viewer, towards us. And the meltwater from that ice sheet makes to this, there's an upper lake, and then it goes over a waterfall and makes it into this lower lake that's the main part of this image. So these lakes are called proglacial lakes. They receive the meltwater from the melting ice sheet fringe. And that meltwater is filthy. Glacial meltwater is not something you want to throw in the bottle and advertise as like glacial springs, pure water. Glacial meltwater is anything but. It's very dirty, got tons of suspended silt in it. You might imagine that if you were able to go to the bottom of this lake and stand on the bottom of the lake bed and dip your hand down in the lake floor, it would silt mud. It would just be really mineral silt, and that's all the glacial erosion that happens up here, and then the meltwater brings down into the lake. Well, we want to take a core of that. So this photograph has our camp. You can actually see a couple of tents, little orange and white dots down here. There's our, and we have a boat, and we come out in a boat with a tripod on it and so on, and we take a core from the bottom of the lake. And the core looks like something like this. From the top, you see a really laminated silt unit. That's the mineral silt, that's the glacial silt. But lo and behold, at some depth, that silt transitions into brown, organic, rich, fluffier lake sediment. And then at the very bottom, it transitions back to silt. And what's going on here is that the basal silt is the regional deglaciation of this area. And then the ice sheet got real small. It wasn't where you see it at the top of this photograph. It was farther inland. So the ice didn't spill over this mountain, and it didn't pour meltwater into these basins. Basins existed, they were lakes, but they were just freshwater lakes, clear water lakes. And then at some point in time, up in here somewhere, the ice sheet re-advanced, this lobe crossed over the mountain, and then it turned back on the meltwater that was able to get down into this basin, and then it covered the bottom of the lake floor with a big layer of silt again. So what we've been doing in my lab is taking cores like this, these special kind of lakes, and radiocarbon dating these contacts so we know when the ice sheet went away and when it came back. And we've been using this information to try to reconstruct ice sheet change in the middle Holocene period. There's one other piece of information that we've been trying to exploit, and that is, if you knew the distance between the present day ice sheet margin and back farther towards the center of Greenland, where is the topographic divide under the ice that when the glacier crosses it, it spills meltwater in here? And when the glacier is smaller or east than that divide, there's no meltwater that makes it into the lake. If we knew where those sub-ice divides were, those topographic basins, then we could actually not just date the ice sheet changes, but we could have some sense of like where the ice sheet was at these time when the lake sediment changes so on radar, this now operation it's all over my sheet surface, shooting radar all the way down to the ice sheet bed. And that's allows us to make this map, sub-ice topographic map of Greenland. And we can zoom in on our little lake areas like here, and we can actually peel off the ice, get a topographic map of the bed of the ice sheet. And that actually allows us to get some distance information about some of these middle Holocene sheet oscillations. So we have been on an intensive campaign to core a bunch of lakes in Western Greenland. And here's Aaliyah here kicking back, watching that helicopter come in. And so here's our coring platform. It's a little tripod on a raft. With a little boat, we can zoom back to shore on once we get a core. So we're pulling up a core right there. So you see the sediment. And this is kind of a shorter one. We could take longer ones than this too, but we just cored into the bottom and we pulled up the sediment core. And now we're going to unconnect the top and then cap the bottom of that core and then bring it back to our lab to study. And here's a couple of graduate students. Allison Cluett is still a PhD student in our department, and here's Aaliyah on the right. Taking a look at one of the sediment cores that we didn't preserve. It was an exploratory core that allowed us to look at the sediments in the field. And we learn more that way, and we can decide where to core next and stuff like that. And in sediment cores, not this one, but another one, when we bring it back home to the lab and we split it open, we see lots of fine scale information preserved in the sediment core. And oftentimes we'll take these cores to a facility that has a scanning X-ray fluorescence instrument. We don't in Buffalo, but we partner labs that do. And here, for example, is the titanium content, which in this particular core picks up with incredible detail every visual sedimentological change that you can see. It just picks it up perfectly with the titanium record in this example. And here's a core that's organic, but with periodic mineral inputs. And then we think maybe that's Aeolian. We still need to do some work on this. And then a pretty big transition, and that's when the ice sheet comes back into the catchment. A lot of times when the glaciers re-advance on Greenland, they're fronted by catabaths that come off the ice sheet. And there's sort of like a wind, strong Aeolian environment front that tracks the ice sheet as it advances and retreats. And so the working hypothesis now is that the mineral stuff is the advancing ice, the increase in Aeolian activity, and then makes it into the catchment and spills meltwater into that lake. Anyway, so back to this question mark time period of the Middle Holocene. This is one of Aaliyah's papers where she made these cross sections across the moraines. So this is that same moraine map I showed earlier. This time it shows the ages of the various moraines on there. And then on the right are these time distance diagrams where we've tried to focus in more on the middle part. So if you look at this blue one here, what is that? Transect B. It has all the moraines on it out here, and then some lakes in here. And so the rest of the information is based on the lakes that we cored. That one and the pink one, we have a little bit of information on this section line A, but then we kind of lose the signal on that one. And then in the green one, we think that it was the ice sheet never retreated inland of its catchment, and that gave us a hint. Basically, it looks like once the ice sheet retreated back to about 7,000 or 6,000 years ago, the ice margin didn't really go that much farther inland, only maybe a little bit inland, and then it kind of came out just a little bit more. Most of the recession was done by maybe 6,000 to 7,000 years ago. All right, well, now what I want to talk about is how we take that information about past ice sheet change and how we somehow can use that to blend it in, to contemporary records of ice sheet change. So that's what this part of the talk is about. And for me, as a glaciologist, it's something I've always wanted to do in my career, is make something more of sampling rocks and digging around in the dirt, trying to do something more with that information we're learning about past ice sheet change. So it's been a real satisfying project for me to get to see our glacial history records be used in such a way that I'm going to talk about here. This is was a really fun collaboration. This work wouldn't have been possible if we didn't get a large group of scientists together to work on the problem. The three components of this research project pursued is ice margin reconstruction. So that's what I've talked about up to now. So that's this circle down here. It's this project that we call the Snow on Ice Project. It's a grant we got funded that started in 2014, 15, must have been 2015. There's an ice sheet model component, and then there's a paleoclimate reconstruction component. And so we use paleoclimate records to drive an ice sheet model, and then we compared that model with our ice margin reconstructions. And so that's kind of where we're going here. Ice sheet models are really important for understanding ice sheets. Like any model, However, they're, you know, they can be semi-useful. They can be really useful if you believe them, but if they're not dated against some piece of reality, then maybe they can be less useful. Here's one example of an ice sheet model that shows the shrinking Greenland ice sheet through the Holocene, from the Ice Age into the Holocene. Here's another example of a modeling study that wanted to know how Greenland ice sheet was during the previous interglaciation, called the last interglaciation, about 125,000 years ago. We know very little about how ice sheet size has changed in the geologic past. The Holocene is a time when we know the most. When we step back to the last interglaciation, we really little, and we don't know how much volume of ice was in the global ocean during what we think was a sea level high stand during the last interglaciation. We really want to know that kind of information, and we turn to models to help us understand some of those topics. So for this effort, I'm sharing with you now a cartoon that we drafted as part of the outreach portion of this grant work that we did. And we call it Scientists Are Superheroes. And so we made these postcards that you're looking at here of 6 or 8 different project scientists and in the various expertises. And we said what their scientific ability was their power. And we brought this to middle school and high school students and to career fairs and things like that. And we're trying to engage with the K through 12 with this kind of superheroes kind of concept. But I want to introduce Josh. Josh is an ice sheet modeler who's sitting at NASA JPL. He was the point ice sheet modeler on this project. And he used a very high resolution model, the ice sheet system model, ISSM, which traditionally before our project had not been used in the paleo. It's only used mostly, it was built and constructed to model contemporary change and invert observational data for bed conditions and things like that. And so the first thing we had to do in this project was retool the model to be run on time scales, on millennial time scales. And Josh was the master modeler when it came to that. So I want to talk about our modeling effort. First of all, what we did was we only modeled the southwestern part of Greenland. Like I said, it was a very high resolution model. And the way we treated the model during like ice ocean interactions and calving, that's not really worked out very well in models yet these days, or at least it wasn't ago. So we decided to model only a portion of the ice sheet where we have the best records of what it actually did in the Holocene and where it's largely land. So it's just sort of a simpler task to model the Greenland ice sheet in this part of Greenland, this quadrant of Greenland. But if you compare ice sheet changes in this part of Greenland with ice sheet changes in all of Greenland, you get a very tight correspondence. That's what this plot on the right shows. So the red line is not our work. It's another study that quantified ice sheet change on Greenland. And they found if we just look at their results in our model domain, you get the red line. And if you look at their results for the entire ice sheet, you get the line. And this is like the rate of mass loss from the 1970s to close to today. And you get a pretty good correspondence. So like if we model just this quadrant, the results might apply to the entire ice sheet. And that's where we were coming from. So I'm going to show you a video of the surface elevation change of this domain of Greenland through the Holocene. So here we go. The time is at 8,000 years ago. And all this flickering of red and blue as ice sheet thinning and thickening through the Holocene. And here we're coming up to today. Actually, I stopped this model version at the pre-industrial period. So the 100 to 200 year interval is pretty boring. The ice sheet was basically in neutral conditions. It wasn't gaining or really losing mass that much. Let's see. I think that's the same slide. Okay. To summarize what I just showed you in a different plot, we can look at this one. It turns out, remember how I said that there were 3 circles? And there was ice margin reconstructions, there was forcing, and the ice sheet modeling. Well, the climate forcing is a little bit tricky in ice sheet modeling. So we forced the ice sheet with 9 different options of forcing. Basically, we had a particular temperature and precipitation that we spread across the ice sheet to force the ice sheet change. But there were some error bars on temperature and precipitation reconstructions over the Holocene. So we ended up running a sort of mini ensemble of 9 ice sheet simulations, all with slightly different climate force. And this is what we get in gigatons of ice change from 12,000 years ago up to basically today to pre-industrial, 1850 actually, 1850 AD. And you can see that most of them, all of them show a big period of ice sheet loss in the early to middle Holocene. That's that warm interval in the Holocene that was warmer than today and driving a lot of ice sheet retreat, all these descending limbs of the, and then some regrowth in the late Holocene. Some of them show minor regrowth, which is what our results support, and some of them show a lot of regrowth, which our glacial geologic results don't support that quite as much. If we turn those data into the rate of mass change, so here is the rate of mass of the Holocene, you can see the values, and the rates, by the way, are per century, gigaton per century, not per year. We felt more confident at the century step, given the paleo kind of coarser aspect of this work. But you can see the mass loss rates down to maybe 5,000 or 7,000 gigatons per century. And then some positive rates, kind of closer to 0 for the rest of the Holocene. So the higher mass loss in the early Holocene is that warm, driven by that warm interval. I'm going to show you a zoomed in part there now. And we averaged the ensemble of 9 here with an error bar. And we compare it with the moraine record that Aaliyah helped produce, get something like this. So every vertical blue bar is the age of a moraine. And when you have the ice sheet depositing a moraine, that means the ice sheet be in neutral or maybe a little bit positive balance in order for it to halt its retreat and build up a moraine, and then the retreat continues. That's what moraines tell us, that must have been a time period of neutral ice sheet mass loss or mass change. And in fact, if you are rate plot with these vertical bars, there is a correspondence almost every time that there's a blip of mass loss that comes close to 0, or in some cases crosses 0, we have a moraine deposited. Similarly, in this interval right here, for example, between maybe 10.5 to 9,000 years ago, we have a big portion of time with only high mass rates, no mass gain or no neutral period in here, and there's no moraine in that interval. So we took this as evidence. Glacial geology sort of validates some of the model results we were getting. What I want to talk about next is bringing those paleo results up to contemporary times. So here is our model simulation of time from 1850 to 2012, and this is now gigatons per year in this particular example. We have a better understanding of temperature and precipitation during this interval. And this is what we think the ice sheet did in terms of its loss rates. So there was a period of loss in the middle of the last century, and then we've been neutral for quite a bit in the contemporary period of high mass loss rates. This is only up to 2012. Then what we did is a final step, and then all together for you guys. The final thing that we did was we took the same ice sheet model and we ran it into the future, following 2 of the IPCC's representative concentration pathway scenarios for greenhouse gas emissions. So RCP 2, which is a low future emission scenario, and RCP 8.5, which is more like a business as usual burn baby burn scenario. And if you take those carbon concentration pathways and put them in global climate models, the climate model output and force the ice sheet model with that. Trajectory of greenhouse gases, and those models show a little bit of deviation. So this is just scattered knowledge in our spread of future mass change as a function of these different concentration pathways. So now what I'm going to do is blend it all together. And I'm going to start by showing you the video. So I'll push play on the video. This is the same video you saw progressing through the Holocene, except for now it's going to end at 2100 AD. So you can see now, not very cold Greenland here. And at the very end, you're going to see a big change. And all that bright red here in this 2100 to 2000 to 2100 interval is the massive amount of surface lowering of the ice sheet in the current century that we're in right now. Here's another look at that. Here are some snapshots. These on the left, there's two centuries that I'm showing you with the most melt of all of the Holocene. And they're compared on the right with the melt this current century under the RCP 2.6. So this is us really doing a good job with emissions. We still see an ice sheet that's as red as it is 8,000 years ago, maybe a little bit more red. And I'm now flick it to the 8.5. And now we see the 8.5 scenario really hammering the ice sheet this century, much, much harder than anything sheet saw during the Holocene. And here now is the 21st century compared to the last two centuries, not the last one century, and then another century in the middle of the Little Ice Age. Ice sheet here, the Little Ice Age has a little bit of a blue tinge to it because it was maybe ice sheet, some warming. And then the 21st century is blasting the ice sheet with a lot of warming. Here's 2.6, and here is RCP 8.5. So putting all that together in a plot space, here's the Holocene, and then here is the current century. So these are all gigatons per century now. The two green dots on top are the RCP 2.6 trajectories, and all these dots down here are the various RCP 8.5 plot trajectories. This histogram in the right is simply tabulating every data point, every century in all 9 of each ensemble in every of all of the Holocene. And what you can see is that even the RCP 2.6 scenario is only, though that kind of melt is only in the Holocene maybe 1% of the time. 99% of the time we've had less melt than even the 2.6. And all of the RCP 8 scenario trajectories for this century exceed anything we saw in the Holocene. So that's basically the punchline of results, and I just wrap it up with a couple of points here. So this is a decade or so of working in West Greenland, glacial geology, my forte, and what I've gotten to do with a lot of great students over the years. We've been able to do these chronologies of ice margin change. Then we teamed up with the modelers and some paleoclimate scientists, and we've simulated the ice sheet change over the Holocene. And we think that that has actually a reasonable match with what we reconstructed with the glacial history, the dirt and the rocks. And so we have actually quite a bit of trusting some of the model output that I just showed. And what the model output shows then is that the Greenland ice sheet of mass loss this century seems to be exceptional in the context of the natural variability that the ice sheet experienced over the last 12,000 years over the Holocene. So I'm going to end it there, and I'll take questions.
Thank you. That was amazing. So, you know, this is the second time I've heard you talk, Jason, and it was just as interesting and fun to listen to. As a matter of fact, when you put my mask on, I'm actually at Queens College today. So, so I got to do protocol. So let's bring it up to some questions. Do people have questions? I would just say unmute yourself and ask away. Actually, okay. So,
I will, Steve.
okay, I have a bunch too. So go for it, Alan.
I actually have a couple, but number one, when I was looking at your dates and when those things were exposed, I was surprised to see that they're very similar to what we suspect we know about the beginnings of the ice sheet that came down here from New York, and yet Greenland's way further north. I would have expected to see much more recent dates. Am I
Right.
missing something?
As far as I understand the New York glacial history, that ice was maybe on Long Island 20 to 20,000 years ago, and then as you say, there are a lot of exposure ages that track its march northward through New England, and that pairs in with some technology really nicely that's been radiocarbon dated here and there, and that puts the ice, I think, at the Canadian border. For 13,000 years ago or something like that.
Yeah.
So I think the glacial record from Long Island up to about Canada is older than what we worked on Greenland, but there are older moraines and glacial deposits on Greenland that are offshore. So most of the history of the Greenland ice sheet that predates about 12,000 is been learned from oceanography and offshore seismic studies and things like that. And so up in that part of the world, Greenland expanded off the island, probably out to the continental shelf break, maybe much in Antarctica, parked itself there during the LGM, and then retreated off the continental shelf, hit land about 12,000.
Okay, it was my error for New York. My other question, is there a difference between the east and west coasts?
Yeah, where we've worked, we have been having a pretty solid available glacial geologic record to work with. On the east side of the Greenland ice sheet, it's a bit steeper and there's a little bit of rain preservation. It's also colder environment. So the ice sheet over there was frozen bedded in a lot of places, and it leads to a more difficult record from the deposits and the rocks that are left behind. But there are records on the east side of the Greenland ice sheet that show it receding through the Holocene also. And not as much work has been done over there, but there are some re-advances that date to like 1,000 years ago. And there's one that dates to like around 10 to 9,000 years ago. And it does look like those line up with some of the moraines we see in West Greenland.
Okay. Thank you.
My pleasure.
Other questions?
I have a quick one. Could you just describe the instrument you used to get your cores, or, well, just the setup and the rigging of that a little bit more? Because I saw it on that kind of funky looking form that you guys had. So I just wanted to learn a little bit more about that.
Yeah, absolutely. They're sort of like homemade coring pins that we fabricated in my machine shop here in Buffalo, but they're based on the pattern that a lot of colleagues use in lake sediment coring. We have a couple of different coring devices we use. The main one to get a lot of those cores is a single drive percussion system with a piston. So it's basically like getting PVC pipes at Home Depot, shipping them to Greenland, and we fit a piston inside like a Sked 40 pipe, 3-inch Sked pipe. And that tube next to a core, of the stainless steel core head part is a slide rod, and it pounds the tube into the mud. We have a cable going up to the surface to the tripod on the cataract, and that piston line goes down to the piston in the core tube. So that's stationary, and we pound over the piston on our way down. And then we pull the thing up with a chain hoist that's used for like an engine block. So we attach a chain hoist to that truck once we're pounded, 10 or 20 feet into the mud, and the piston's at the top of the tube, and the tube is now beyond the piston. Now we secure the piston line to the core head line, attach it to the chain hoist, and pull the whole thing up together with the piston in the bottom, and we retain the mud in the PVC pipe. We get up to the surface, and then we ship it home and cut it open. Does that help explain at all?
Oh, yes, very much so. Much more, and I'm very satisfied. Thank you very much.
Okay, good.
Great question. Other questions? Okay, so let me ask a question then while people think about this. First of all,
Hey, Steve, we actually do have a couple of questions in the chat window.
oh, we do. Let me go to chat. Okay. So let's see what we got here. Oh, okay. So Diana, okay. So she asks, I believe it was the first few slides, but what was the cause for the ice sheet balance between the receding and accumulation in the 1980s to the early 2000s? Oops.
Between and accumulations, more or less the ice sheet was in balance until the 2000, basically the current century we're in. I have this question too. You know, we've experienced quite a long period of global warming up to that point in time, yet the Greenland ice sheet was in balance. In particular, if you look at Arctic climate records, it looks like the Arctic started to warm up mostly maybe in the 80s. But there is an interesting sort of health that the ice sheet maintained until 2000 or the early 2000s. And that's a good question. I don't know the answer to that. I suspect it might be some balance between land thickening and peripheral thinning that's actually happening on the ice sheet today, because of maybe an increase in moisture in the Arctic and you actually have some inland accumulation that's increasing. And that just happens to be counterbalanced by all the dramatic thinning at the edges of the sheet. And the peripheral thinning is winning over the inland thickening. It's possible it took a decade or two for that peripheral thinning to really beat out some of the inland thickening, but I'm not totally positive. I'm also not totally positive I answered your question, so definitely.
Other questions?
Hey, Steve, may I have a question?
Absolutely. Go on, Trey.
Jason, I'm Trey. Thank you so much. I'm not only learning science, also learn how to teach. Excellent. So for this modeling, ice sheet modeling, this is 3-dimensional, and what the time step is?
Yeah, it's a 3D model. It's the horizontal resolution on the surface. It's an adaptive mesh thing. So if you see the ice sheet, there's huge pixels. And as you get toward the margin where there's more action and more topography, the pixels come down to about 2 meters. So it's a changing mesh. And then there are some vertical dimensions. One of the things we did to run it in the paleo on long time scales, since it's a high order complicated model, is that we were able to figure out that rather than having a lot of layers in the ice sheet, we could boil it down to 2 or 3. So there's not as much layering as in the higher resolution versions. The time steps ranged between around a century to maybe 200 or 300 years. Wait, let me think, maybe down to 80 years up to a couple hundred years or something like that. In the beginning, we did that sort of coarse way, and then eventually we settled on the 100-year time step so we could output the rate of change at the centennial. We decided that that was something that resolution on the temporal side was something we were comfortable with.
So another question, it's this ice sheet on the land. Is there some, this CS? So if there's S, the function may be different from this S sheet, right?
Yes.
Is the modeling consider this connection
No,
difference?
it's a really good question. This model that we used did not have really any kind of elegant of ice-ocean interactions. The ice sheet modeling community is struggling with how to, and for a good reason, it's a big challenge. Calving, the influence, the buttressing effect you can get from sea ice, as you're mentioning, or in Greenland, what's called the melange. So sea ice frozen in icebergs, that can act as a really big buttressing effect on the marine termini that are calving into the ocean, and don't, I would say, perform well in modeling those interactions. We tried to avoid that issue mostly by working in a land-based part of the ice sheet, where the ice sheet was mostly always on land and didn't have much interaction with the ocean. There's a little bit of interaction with the ocean in our domain, our model domain for sure, but a small percentage of our model domain. So I would say our model performs poorly in those marine areas for that reason. That hasn't been modeled highly successfully yet, I would say. So it's a really good question you ask.
So I have a last question. So for your curve, show us about, Greenland mass variation for 2020. There's a big dip. I think another in June, right? Yeah. So yeah.
In this one or earlier?
No,
one?
not this one. Early one. It's 2020. It's for the 2020. Yeah.
Like
not the modeling, not the modeling, just data.
Okay.
Beginning almost. Yeah.
Okay.
Yeah. So there's a big dip. May there's a mass loss is the last big dip in June, end of June. So this oscillation must be related to temperature. Have you linked this to like monthly temperature or daily temperature for this?
Yeah, I see. That's a good question about the melt record and how that's linked to temperature. Clearly it's temperature, but I think there's a lot of meteorology that is beyond me to understand. But when you get into some of those pressure systems and you stall warm air over the ice sheet for long periods of time, you can get some of those big prolonged melts that maybe you're referring to in the 2020 melt season. I think a lot of that is the meteorological conditions that gives to a big slug of warm air that can hang out over the ice sheet for a long time. And that might be related to sea ice changes, and there might be some more persistent other patterns that are starting to emerge with smaller Arctic sea ice and stuff like that. But that might be something you know better than I do.
Thank you.
Yeah.
There's a time lag. Yeah.
So we have some questions from students, which is great. From Gottfried, historical and projected models display an overall downward trend, yet there are points where the trends go up, ice gain. Why is this?
Yeah, and even in the projected part, that's a super good question. Why? With it, just as I summarize what this person's asking, in the future, when greenhouse gases are basically just going up, why is there oscillation mass loss? Like, why is it not just steadily going down? And I think that's just the climate, that's weather. I think climate system, these are complicated global climate models, and you feed in a greenhouse gas forcing, but there must be some other prescribed conditions that allow these models to operate. Maybe there's like ENSO variability in them. Maybe they have volcanoes popping off now and again. There's maybe some other aerosol loading. So I think that these models are very sophisticated, and they're trying to get all the naturality that's within our climate system So if I had to guess, it's because there's a lot of natural variability and human forced variability in the climate. So it makes a temperature projection that then is controlling mass loss rate. It's not just like a linear smooth, but it's the noise of the climate system is what I'm suspecting.
That was a great question too.
Yeah,
so a
really.
couple more students. Can you hang on for a couple more questions?
I'm
Jason?
good.
Okay.
Yeah.
Great.
Oh, yeah.
Okay, so this one's from Inva. So she read your paper because she's a good graduate student, and she was wondering if it's possible to construct a model of the Greenland ice sheet mass loss if low carbon emissions are applied, accounting for a lag time. Approximately how long would it take for the Greenland ice sheet to start slowing the rate, showing lower rates of retreat? And finally, is the rate of the ice sheet mass loss in Greenland faster than Antarctica? And if so, why? Wow.
Yeah, really good questions.
Yeah.
Let's pick apart the first one. Oh, I love this Zoom interface because I can see the chat and I don't have to remember all the parts of your questions. Perfect.
Exactly.
It's great for the speaker. So construct a model if low carbon emissions applied. How long would it take for the GIS to start? Yeah, like really slow. Well, in the slide I'm showing right now, in these green ones, you can see actually that if society, if humanity energy diet and like really does well with cutting down emissions, you can see the RCP 2.6 scenario ice sheet change, one of them is coming right back up to zero.
Yep.
So by 2100, cumulatively through this century, even they'll have lost a lot of ice. But by the end of the century, one of these babies is coming right back up to zero. So I think that kind of answers your questions if I can, that even RCP 2.6 by the end of the century, we're starting to come back up to a healthy ice sheet. So the ice sheet might take a big hit, but it might start to equilibrate in a new state that's around 2100 AD if we follow that emission scenario. And then is it faster than Antarctica? Well, it currently is because it's really getting hammered by warming. You know how the Arctic, you maybe have heard that the Arctic is warming about 2 or 3 times the rate of the rest of the planet. So the Arctic, the whole planet, we're cranking the oven temperature. In the Arctic, we're really cranking the oven temperature. So the Greenland ice sheet up there is just like baking in all this extra heat. And so it's melting really fast. And that surface melt isn't taking place a lot in Antarctica. What's really nailing the West Antarctic ice sheet is the warm ocean water and mining under the ice. And there's going to be a lot of calving down there that might be irreversible as the ice sheet gets into deeper water behind where it is today. So there's a lot of concern about the Antarctic ice sheet going forward in the future. But I think right now Greenland is just winning because maybe a little longer for those changes to take place in Antarctica. There is very fast change happening in Antarctica, but it's in a very specific part of the West Antarctic ice sheet.
Great question. Wow. Yeah, and so like Antarctica is Greenland seems to be getting hammered both ways, from the atmosphere and from the warmer currents coming in. And it seems like most of the melting in Antarctica is coming actually from the warmer ocean currents. The temperature really hasn't risen as much as up near Greenland. So it's only getting hammered in one way, but it's bad. So I have another question from a student. Okay, so this is from Amanda. And so in the paper that our graduate students had to read, it was mentioned that some of the dynamics are more marine influenced in other regions of the ice sheet. How is the region where your group does analysis relative to the whole ice sheet if there are different dynamics? And I had a similar question. So.
Yeah, man, that's a good question. Really, really good question. And because it's definitely true. Like, okay, so I made the claim that like we're modeling a silver ice sheet, and then we're kind of trying to claim that, well, this is representative of the whole ice sheet. But the rest of the ice sheet is much more influenced by marine dynamics, and we're modeling marine dynamics. So could we be missing something because we're not modeling ice-ocean interactions in our realm So maybe it's actually not very applicable, our domain versus the rest of the ice sheet. So I applaud the question, really, really good question. And I'll have a two-part answer. One is that, like in the plot I showed where we compare the rate of ice sheet change in our domain with the rest of the ice sheet, they look pretty similar. So at least today, on timescales, it looks like what we model in our domain is proportional to what the whole Greenland ice sheet is doing with a pretty high R². But it is possible that on longer millennial timescales, that relationship between our domain to the whole ice sheet isn't as strong, sure. And we don't have an answer to that right now. So what we're actually trying to do as a next step is model the entire ice sheet, writing a proposal to the NSF to try to continue this work. And we're calling what we've done so far our pilot study in this simple domain, and do now is expand it to the whole ice sheet to ask the very question that you raise, exactly that question. And unlike 5 years ago, we do a bit better of an understanding of how to treat calving in these models, and we're going to try to do a better job at ice ocean interactions, so that, who knows, we might fail at this proposal and never get money to do it, but if the winds are in our favor and we are able to do it, we'll do it exactly for the reason asked, just to basically see if our results really do apply to the whole ice sheet. Well, we can answer that by trying to model the whole ice sheet. It's a really good question.
Yeah, great, thank you. And so any more student questions? Okay, anybody else? Because I would just like to ask two quick questions. One of them is that I'm not really a gigaton expert when it comes to ice. And so how does this relate, your gigaton loss with the different models, the different IPCC models? Well, how do you, can you convert that over to ice mass loss, and actually sea level in this case? How much sea level would be gaining and rising due to this ice loss?
Yeah, good question. So there's a relatively easy conversion of gigatons of sea level equivalent, and that is that for every 361 gigatons of ice, that's 1 millimeter of global sea level rise.
Okay.
And if you do math, it looks like the Greenland ice sheet, if you follow the RCP 8.5 scenario and you sort of average out the various red lines,
Right.
You get about 9 centimeters.
Okay, for the whole ice sheet or for your section?
That is for our.
Or for your section, okay.
Yeah. So.
Yeah, so any projections on extrapolating that out to the whole ice sheet?
So that's a good question, because we wouldn't want to do it where we take the aerial extent of our to the aerial extent of the ice sheet.
Yeah.
But what we want to understand is for any given gigaton of mass change in our domain for the whole ice, that relationship, and it ranges between maybe 30 to 50%, 25 to 50% in that realm. So we could take that 9 and multiply it by 2 or multiply it by 4.
Okay.
And so we're maybe in the 20 to 30 centimeter range for the whole ice sheet according to these results.
Yes, we're talking about
and something we gotta keep in mind. So what is that? Maybe that's almost up or something like that. And something we got to keep in mind is that what we see coming from Greenland is maybe about a third of what we see the global, like mountain glaciers and Antarctic ice sheet and thermal expansion. I think these days Greenland is about a third of the overall sea level contribution. So if that ratio held and we had maybe a foot coming from Greenland, that could be maybe 3 feet globally.
Exactly. Okay.
Hey, Steve.
And
Steve?
so, yes, hello.
I got a question. This is Tim E.
Hi, Tim. Go ahead. Absolutely. Jump in.
Hi, Jason. A wonderful talk. I'm a hydrologist in the department, but I also have an interest in glacial geology. Really looking forward to Aaliyah coming to the department.
Great.
Marvelous talk, really lucid. I did have a question about the beryllium age dating on the moraines.
Yeah.
You mentioned that obviously you're selecting the boulders that are thought to have remained in place since the ice retreat, but a number of these boulders have to have uncovered by subsequent erosion. And it's a little hard to get a handle on that. And you mentioned that, well, you didn't mention that actually might be a cause of some of the spread in the beryllium age dating ranges. I was wondering if you have any independent check on that through lichen age, like dating on the rocks or anything like that. Any sort of way of cross correlating or cross confirming some of your results for the beryllium dating?
Yeah, good question. Exposure dating has done a lot of good things to the field of glacial geology in terms of allowing us to get a chronology where we weren't before able to. But on the other hand, there are quite a number of complications with the method, and certainly you point out one of them. I mean, what are the that like some boulder that the glacier plops down is still there 10,000 years later unmodified? Like, that's pretty rare to find a sample that experienced any change. Whether it's like because it's on the top of a pile of dirt that's like settled through 10,000 years, or whether the little bit of physical erosion of the grain to grain surface of the granite boulder itself. There's other complications like, is it ever covered with a giant thick pack every winter, and does that reduce the beryllium-10 accumulation? So there's certainly a lot of complications with that dating method. And so a two-part answer here. One is that we try to date a lot of boulders per moraine. That's why we don't just do one. Is that if we date a bunch of, we only choose the most stable large boulders that we can find. So the ones most likely be representative of the true age of the moraine. And then if we repeat that 5 or 7 times and we go to different parts of the moraine, if moraine degradation was a big influence, we would expect to see quite a bit of scatter, because what are the chances that each boulder a kilometer away would have the same history degradation? So if we date a bunch of boulders and they all produce a clustering age, that gives us confidence that that's probably a good approximate real moraine age and not a reflection of some of these processes. The other thing is that we have in some places matched it with radiocarbon dating. So where the glacier maybe rode over marine sediments and put a shell in the moraine, and then we date the boulder on that moraine. Or the glacier retreats from the moraine, there's a lake right behind the moraine, and we can core the lake and get the basal radiocarbon age and compare that with the boulder on the moraine. So we've done kind of pairing, and a lot of it lines up. Like, we do have radiocarbon support for the beryllium dating method in some of those places.
Great. And so, so before we end, I do have a kind of a semi question. It's actually geared toward the students, because in my introduction to you, I didn't really mention some of the biggest news that we had, that your former PhD student, Aliyah Lesnick, is coming to Queens College. Alan mentioned it a little bit early on, but not explicitly. And so for all the students, some of the students have dropped out, but most of the students still here. So in next year, Dr. Lesnick, or Aliyah, will be here at Queens College. And so my question to you is that, I kind of know the answer because I saw her talk, but is she going to be continuing lots of the work that she was working with you with cosmogenic grading, dating, and sediment cores from different parts of the polar areas?
I really hope so.
Okay.
It would be great to work with Aliyah more. We're currently, the piece of work that we're currently working on together is in Alaska, in Southeast Alaska, where we're working on the ice sheet history, that we're the peopling of the Americas. It's this really, really cool problem. And we were in the field together after her PhD, some samples over there, and she's working on some of those samples as part of her postdoc up at UNH. And so over there, we're still currently collaborating, and she did write a proposal to do some lake sediment coring work in Alaska on some proglacial lakes from mountain glaciers, and she's also exposure dating over there too. So yeah, I mean, she's going to be using the same techniques that you saw in my talk, And I really hope that we have a chance to continue collaboration. It's been really great working with her.
I would enjoy having you collaborating with her, so you can come down once in a while too. And so for all the students out there, so if you're thinking, if you watching this talk, you are, my goodness, I would really love to explore, do geology like the way Jason's doing, you know, going up to Greenland and Alaska and seeing, you saw the pictures, how beautiful they are, you saw the science that he's doing. Next year, we're gonna have basically his former student coming here, and she's gonna, and I remember her talk, she's got a lot of projects that she's either already got funded or will be having funded. And I'm sure she'll be taking students into the field with, like the way you did with her. Whoops, did I break up? Hello?
You're back now.
Oh, shy. How much did you lose? I was just giving a little speech. So just to repeat myself, I do that sometimes. So the students, you know, for future students, whether you're undergraduate students or undeclared master's student, if you enjoyed what, and we're excited by what Jason Briner is doing, we're going to have his former student here doing similar work, and I'm sure she'll be taking students into the field the way Jason was when he took his students up into Greenland and other places. Okay. So with that, if there's no other questions, are there any last ones? Okay. I wanted to kind of finish off with that. I want to thank you again, Jason. That was amazing. I saw it for the second time, still loved it. So bravo.
Great.
And so let's stay in touch. You know, you have the field school. I'm sure that you have other results coming up in the future. We would love to stay in contact with you. Absolutely.
Sounds great. Yeah, and it's too bad I couldn't in person this time, but maybe in a new world and new future that'll happen again soon, I'm sure.
Yeah, let's hope, you know, later in 2021 things can get back to normal and you can come down to New York.
Yeah, that'd be really great.
That'll be great. Okay, well, thank you again, Jason. Thanks for everyone for coming today. You saw a great talk, and for the people who didn't make it, they missed out on something fantastic. So thanks a lot, Jason. And what do we stay on for a couple of minutes afterwards?